In our next video, we're going to talk about the relationship between the volume of a gas and the temperature of a gas. Okay, and for me, a real easy way to think about this is what happens when you put a balloon in the freezer. Okay, the pressure hasn't changed. The pressure inside the freezer is about the same as outside the freezer. Okay, but what happens to the size of that balloon when you put a blown up balloon into the freezer is, of course, it gets smaller. Okay, and we're going to see that right here. I'm going to put some gas particles into our container here. Okay, and when we do that, I'm going to make the pressure stay the same. And then I'm going to slowly start to raise the temperature. So down here at the bottom, see the little flame popping up here. Notice our volume. What is our volume doing as I start to raise the temperature? Of course, that volume is getting bigger. That as the temperature goes up, you can see it even more. Okay, and I'm going to stop it. Okay, the volume gets bigger. Okay, and then as I lower the temperature, what happens to the volume? Of course, the volume gets smaller. Okay, so that's like you put it in the freezer. Okay, and what happens is the molecules, the gas particles, are moving slower. And as they're moving slower, they're hitting the walls of the container less often and with less force. Those are kind of the two reasons why temperature has such an impact on the volume. Because as you raise the temperature, the gas particles start moving faster. You can kind of see that there. And as they move faster, they're hitting the walls of the container more often. And because they're moving faster, they're hitting the walls of the container with more force. And as you cool them down, you can see that as the temperature of the gas goes down, so does the volume of the gas. Okay, and what that leads us to is it leads us to the idea of what's called Charles' law. Now these names, Boyle's law, Charles' law, you don't need to remember them, okay, the names of them, but you should understand what was the thing he asked us to remember about Boyle's law is the water bottle. The empty water bottle, you squeeze it, the pressure goes up, the lid goes shooting off, okay? The thing that help you remember Charles' law is a balloon that's put into a freezer. When you remove the balloon, it's much smaller because its volume has gone down. Now, mathematically, remember that Boyle's law was P1 V1 equals P2 V2, and that was an inverse relationship, which means when the pressure goes up, the volume goes down, and vice versa. Okay, with Charles' law, we just said, when you raise the temperature of a gas, what did the volume do? The volume got bigger. And when we lowered the temperature of the gas, what did the volume do? The volume got smaller. Okay, that's called a direct relationship. Okay, so I think that's up here. Yeah, it's directly proportional instead of inversely proportional to each other, like in Boyle's law. So there's the volume and the temperature are directly proportional to each other, which means that with Charles' law, when the volume goes up, the temperature goes up. If the temperature goes down, the volume also goes down. Okay, that's a direct relationship. This is true, and this is true. Now, the tricky part about Charles' law, number one, is these temperatures. Okay, when you do the math with Charles' law, the temperature must be in Kelvin. Okay, if they give you a temperature in Celsius, let's say they say this is 25 degrees Celsius, and they say at the end, after we change this volume from 5 liters to 45 liters, what's the temperature in Celsius? You still, so if they want the answer in Celsius and they give you the number in Celsius, you still have to do the problem in Kelvin. Okay, it must be the Kelvin temperature, because the temperature in Kelvin, and remember, is the real temperature. It's a measure of the energy, where Celsius is just a more convenient scale that, again, most of the world uses other than the United States. So temperature in Charles' law must be in Kelvin when you're doing the actual math. Okay, let's take a look at what this looks like. Okay, so let's use that balloon from earlier. A balloon is blown up to a volume of 475 milliliters. Okay, so that's my initial volume. And it's at room temperature, 25 degrees Celsius. As soon as you see that, immediately cross it out and write the temperature in Kelvin. Okay, so that's our initial temperature, T1. The balloon is then placed in dry ice, which has a temperature of negative 78.5 degrees Celsius. Now here you might want to use a calculator. Negative 78.5 plus 273 equals, again, get rid of that Celsius temperature, 194.5 Kelvin, and that's our final temperature. Okay, and they want to know, what is the volume of the balloon? So what are they asking us for? They're asking us for the final volume. So what do we do? Just like with Boyle's law, what do? We plug the numbers into the equation, and then we solve for the unknown. Okay, so here's our V1 right here. It's 475 from there. Our initial temperature, remember, was that temperature in Kelvin, so there's T1. V2 is what they're looking for, so we write that as V2, and then the final temperature was 194.5, so that is T2. Okay, now when you have, just like in math, when you have a fraction, what do you do to solve that? You cross multiply. So I'm going to cross multiply, which means I'm going to multiply the 194.5 up to here, and notice what it becomes. Okay, that's what cross multiplication is you take the denominators on both sides and then you multiply them on the opposite sides. So notice the 298, I multiply it with the V2. And now it's just a basic algebra problem where we have to get V2 by itself. So we divide by 200, we divide both sides by 298 Kelvin. You can see that here. And then you can see Kelvin over Kelvin is going to cancel. And we're left with 475 times 194.5 over 298 equals 310 milliliters. Now, does that make sense? Does it make sense that it was at 475 and you made it colder, and so now it's at 310? Absolutely yes. Okay, certainly that is a valid, it makes sense. Okay, example 2. The gas volume in an aerosol can is 1.5 liters at 25. What would the volume be if the can were heated to 450 at constant pressure? Again, notice the temperatures are in Celsius. You got to immediately put them into Kelvin. So that's 298 and 273 plus 450. 273 plus 450 is 723 Kelvin. Okay, and so now we use the gas law. 1.5 liters is our V1 over 298 Kelvin equals, again, they want to know the volume, so V2 is our unknown, 723. And then again, I'm going to cross multiply and I'm going to divide. So you might want to pause it at this point, see if you get the same answer as me. Okay, so I'm going to take 723, multiply by 1.5. So I'm going to move the 723 over to here. The 298 comes over here. And then to get V2 by itself, I've got to divide by 298. And when I do that, I get a final answer of 3.6 liters. So our volume went from 1.5 liter to 3.6 liters. Okay, and that's a lot of times, if an aerosol can gets too hot, what does it do? It explodes. And why does it explode? Because it needs more volume. It needs more space. Those particles start moving so fast with so much energy that if you throw an aerosol can in a fire, a lot of times it's going to explode because it doesn't have 3.6 liters, but it needs it. And so it's going to explode because that pressure is going to grow so much. Okay? All right, example 3 says a fixed quantity of a gas at 23 degrees Celsius, again, 296 Kelvin right away, exhibits a pressure of 748 torr and occupies a volume of 10.3 liters. Calculate the volume if the temperatures increase while the pressure remains constant. Again, that's an important part there of Charles' law, is the pressure has to remain constant. Why did they give us that 748 torr? Just to mess with us, just to try to trick us. Okay? So 273 plus 165 is 438 Kelvin. So we've got our temperatures in Kelvin. We're not using that 748 torr at all because it tells us the pressure remains constant. We have to read that very carefully. So V1 is 10.3 liters, 296 Kelvin. Our new volume is again our unknown, and then 438 Kelvin. Okay, I'm going to do this one a little bit quicker. 438 times 10.3 divided by 296 equals 15.2 liters. Done. Okay, example 4. Okay, and this is our last one here. So in example 4, it says, a sample of gas occupies a volume of 1,248 cubic feet. Ugh, never heard of that before, but that is a way to measure volume. It's at 0.988 atmospheres and at 28 degrees Celsius. Calculate the pressure of the gas if its volume is decreased to 978 cubic feet while its temperature is held constant. The most important part in that whole question is right here. Temperature is held constant. We've learned two different equations. P1V1 equals P2V2 and V1 over T1 equals V2 over T2. If the temperature is held constant, can we use this equation? We can't, because the temperature is constant. It's the same on both sides. So that's a good indicator. Oh, it's not a Charles' law question. This one must be a Boyle's law question. So the volume is 1,248 cubic feet. So I'm going to use P1V1 equals P2V2. Okay? And yes, we've got a weird volume we've never seen before, but watch, it's going to disappear anyway. So what's our initial pressure? And that's where understanding these units is really important. It never says the pressure is. It just says it's at 0.988 atmospheres. You just have to know, oh, atmospheres is pressure. So it's 0.988, 0.988 atmospheres. The initial volume is 1,248 cubic feet. Our final pressure is what they're asking you for. Calculate the pressure. So P2, and then times V2, the final pressure is there, 978 cubic feet. And so to find P2, we divide by 978. So 0.988 times 1,248 divided by 978, lots of 9s and 8s there, not squared, gives me an answer of 1.26. And again, by dividing by those 978 cubic feet, notice that cubic feet and cubic feet cancel. So the answer is just in atmospheres. Okay, the only unit that must be a certain one is temperature. And we talked about that. Temperature has to be in Kelvin. Okay, last one. At what temperature in degrees Celsius is the volume of the gas 1435 cubic feet if the pressure is held constant? So now pressure is kept constant, which means we can't use Boyle's law. Now we have to use Charles' law. Okay? Because if pressure remains constant, then P1 and P2 are the same thing. So what was our initial volume again? Again, it occupied a volume of 1,248 cubic feet. So 1,248 cubic feet is our V1 over T1. What was our initial temperature? 28 degrees Celsius plus 273 equals 301 Kelvin. Okay, and again, notice that even though they're asking me for the temperature in Celsius, and the temperature up here is in Celsius, when I put it into Charles' law, it must be in Kelvin like I did here. Okay, and then our final volume is 1435, so 1435 cubic feet, and then the final temperature is our unknown. Okay, so at what temperature, and again, remember they want it in Celsius, so when we get done, we're going to have to convert it back to Celsius. Okay, so once again, I'm going to cross multiply. The T2 comes up here, the 301 comes up there. And remember, I have to get T2 by itself. So the equation now looks like this. After I cross multiply, the equation looks like this. And then we've got our 1435 cubic feet times the 301 Kelvin. Sorry, running out of room there. Okay? And so to get T2 by itself, we've got to multiply both sides by our 1,248 cubic feet. So I'm going to take 1435, multiply by 301, divide by 1248, and hopefully I did it right. T2 cancels, cubic feet cancels. So notice that Kelvin right there is the only thing that's left. So that's 346 Kelvin. But to get it back to Celsius, I've got to take 346 minus 273. So our final temperature in Celsius equals 73 degrees Celsius. Okay, and that is Charles' law.